Hello student, welcome once again in the series of basic ultrasonic testing. So in the previous lecture, we start this topic basics of ultrasonic testing and then we first saw the basic properties of ultrasonic waves. Then we learn about different type of ultrasonic waves. So now in today class, I am going to tell you about one more wave which is not covered in the previous lecture. So let us talk about this type of wave. In previous lecture, I have already defined you in surface or interface various type of particle movement and that would give rise to the type of ultrasonic wave. So the wave are rising due to the particles movement. For example, you could have elliptical or other complex kind of path in the movement of particles as the sound moves through the medium. So this kind of elliptical as you shown in a picture or other complex vibration which are generated on the surface are known as surface or Rayleigh waves which are generated in relatively thick sample. Okay, so Rayleigh waves are especially used for thick sample. So let us say if sound is moving in this direction, so you can have a particle movement path like an electrical path as shown in a picture. So this will be the movement of the particles and through this kind of movement you will generate the motion for the waves in the horizontal direction. So this kind of wave which are generated at a surface or interface in a thick material, they are they are known as surface or Rayleigh waves. But in case of thin plates, you could have some other type of waves being generated, which are known as plate waves. And this can be further divided into two categories as shown in image. One is known as the lamp and the other one is known as love. So lamp is the component of the vibration which is perpendicular to the surface and love is parallel to the plane layer and perpendicular to the direction of waves. So these are two different type of plate waves that you can find on thin plates. One is lamp and the other is love. Further, lamp is divided into two parts, that is symmetric and asymmetric. In case of symmetric lamp, it is also known as shown in figure, first two waves are symmetric waves. So it is also known as extensional waves. And in case of asymmetric, this is shown in image, this is a flexible mode, the last two one. Okay. So these are the different type of ultrasonic waves. Our primary concern for ultrasonic testing for NDT would be the longitudinal and transverse waves. So we will talk more about them only when we talk about ultrasonic testing as a NDT method. So now let me tell you how these ultrasonic waves are used for doing NDT. So the basic principle behind this is fairly simple. We also know about reflection of sound waves or the echo of sound. For example, for our understanding, if you talk loudly in an empty room, the walls will reflect the sound and you will get an echo. So while doing ultrasonic testing, these ultrasonic waves are sent into the sample and when these waves are reflected back, they are collected by a transducer which finally will generate the signal. If there is any defect, if there is any defect are present in that sample, so this defect will also act as a reflector which can reflect the sound waves. Okay, but in that case the reflection interface is much smaller compared to a wall. So that means the energy which is there in the reflected waves should be enough for the transducer or the instrument to collect this signal back. Okay. The energy in the transmitted sound waves will depend on the sound pressure, which is created by these traveling waves. When the wave is traveling, so some pressure is created. So you might know that sound waves travel through a medium by oscillatory movement of the atoms or the particle, and this movement is due to the local pressure which is created by sound. So this pressure is the excess pressure above the atmospheric pressure. So when sound waves are traveling through a medium, this local pressure provides some movement to the atoms, and due to the bonding between the atoms, it creates an oscillatory movement which in turn will create a wave. So that is how the sound waves are propagate through a particular. So let us say this local pressure which is created by the sound is P, and it provides a velocity to the particles or the atoms which is Q, because this will provide some movement to the particles of the atom. So let us say the velocity of the movement is Q, so P will be proportional to the Q. So we can write P proportional to Q. So as from the equation, you see that higher the pressure, higher will be the movement between the atoms. Now, if we introduce this proportionality constant, then we can write the equation P equal to ZQ, where Z is known as acoustic impedance. So this is nothing but the total resistance to the movement of sound waves through a particular medium. And the energy of the transmitted beam, the energy in the transmitted waves, it is denoted by the capital E, is again dependent on the pressure P, as shown in the formula in image, equal to P square by 2 rho V, where in rho is the density of the medium and V is the velocity of sound wave through the medium. So you should have enough energy first of all in the transmitted sound waves which go to the sample, and then when it is reflected back, that reflected waves also should have enough energy so that the instrument which is used for doing ultrasonic testing should be able to capture it. If you want to get an expression for P and Q, so you see the image shown in that particular slide, we have a sine wave of a lambda wavelength, and to complete that cycle it required time t. The angular velocity of that wave is omega. At the other end, having an amplitude of y naught. So the wave is represented by an equation like y equal to y naught sine bracket में omega t minus kx. So if this be the wave, so where y naught is the amplitude, which I already explained to you. Okay, and the angular velocity is represented by omega is equal to 2 pi f, where f is the frequency and k is known as the wave number, which is equal to the k lambda is equal to 2 pi. Okay, so lambda is the wavelength. So if this be the wave, then the velocity which is given to the particles or to the atom q is q equal to dy by dt. Okay. So we differentiate that equation y equal to y naught sine omega t minus kx. So we got the expression. So we can write q equal to omega y naught sine omega t minus kx. So this is the effect of sound waves. When it travels through a medium, it provides this velocity q, and the resistance to the movement of sound wave is given by that parameter acoustic impedance. So based upon this transmitted beam energy, it will enter a particular sample or a particular medium, and then when it encounters an interface, a part of this sound beam will be reflected back, and the energy of that reflected beam That will depend on this particular parameter, acoustic impedance, as to what is the change of impedance across that reflecting interface. So that is what will decide it, the energy in the reflected beam, and if the energy is enough in this echo or in this reflected beam, then you can use an instrument, a transducer, to capture that energy and convert that into a signal which can be shown in the display of the system. So that is how you will get to know about presence of defects. If that reflecting interface be a defect, so that is how the basic principle is behind this particular technique. It is a fairly simple one. It is based upon the reflection of sound waves from discontinuity, which provide a reflecting interface to the sound waves which are propagating through a sample. Acoustic impedance is a very important parameter. So, which is the total resistance of the movement of a sound waves in a particular medium, and this is the ratio of sound pressure and the velocity of the particles or the atom inside the medium. How this particular parameter will decide the energy in the reflected beam, because that is what is our concern for this particular technique. We need to capture the echoes or the reflected sound beams which are coming out from the sample, and whether you would be able to capture it or not, that would depend upon the energy which is there in this reflected sound beam, and this energy in the reflected beam will depend on the change of the acoustic impedance Z across that reflecting interface. So what basically happens when the sound waves encounters an interface or discontinuity? These discontinuities or the boundaries will give rise to a change in Z, and this change can be detected when the sound waves are reflected from these boundaries, because the energy in the reflected beam will depend on this change. So if you have two medium 1 and 2 with the acoustic impedance Z2 and Z1, so across these boundaries there is a change in the impedance. If you have sound waves coming and getting reflected back from this boundary, then the energy in the reflected beam that would depend on this change. So we can write this energy in the reflected beam is proportional to Z2 minus Z1, where Z2 and Z1 are the acoustic impedance. So I am going to show you as to how, or explain you how exactly this energy is related to this change. So now let us say we have a medium, one medium as you shown in that picture, the dark color, that is your medium through which one sound wave is incident and pass. Some of the waves are reflected back. So the sound waves are moving through it at a particular velocity. So this is the incident wave. We will call that as first part. If you see on the left hand side, there is a first part and in its paths by an arrow. If the wave encounters an interact, that means if there is a change in the medium or there is some discontinuity, then this acoustic impedance will change. So let us say in medium 1 it is Z1 and medium 2, or across this interface, across that particular interface of medium, it is Z2. So when there is a change in the impedance and when the sound encounters an interface, a part of the sound wave will be reflected and a part of it will be transmitted. So this is the transmitted wave as we shown in the previous slide in the image, and this one in the is the reflected. Let us call them as T and R respectively. So the energy of this reflected beam, which is our concern, for doing NDT will depend on what is the impedance change across the interface. So this interface could be the defect itself. When the sound waves encounter the discontinuity, it will reflect a part of the sound waves, and the energy of that reflected waves will depend on the change in the acoustic impedance across that interface. And that can be calculated because across the path of the sound being, the is whole thing is continuing in the sense, if I be the incident beam as we have write or written, then you can write this qi plus qr is equal to qt. This parameter q will be defined, that is the velocity given to the atoms, or we can also say that pi plus pr equal to pt. So this is across the interface. Since this is continuous, these individual components can be estimated, and the fraction of energy into the reflected waves would depend on. So if we call that as RE, so that would depend on the change in the acoustic impedance. So we can represent fraction of energy reflected equal to Z2 minus Z1 upon Z1 plus Z2. So if you have enough energy in the reflected wave coming out from the flow, then this can be easily captured through an instrument, and then you can generate a defect signal and get the indication about the presence of defect and flaws on a given sample. So this is how the ultrasonic waves can be used for doing NDT. So this is primarily based on the sound echo or reflection of sound waves. Reflection of ultrasonic wave from the discontinuities which present a scattering interface for reflecting the sound waves. So if you have the instrument, you that means you can capture this reflected beam coming out from the sample or coming out from a defect, then you can use that to do NDT and get indication of defect. So dear student, for any query, please write me on my mail ID rohitsau87@gmail.com, rohitsahu87@gmail.com. Thank you. Thank you. To be continuing in the next session. Stay safe, stay home. Take care.